Beautiful.
Okay, well then we'll begin. So thanks very much. My name is Scott Cordella. I'm an adjunct professor here at PVCC. I work for my colleague Ken Wellborn, and we're also joined by Henry Weinshank, who is, I would call, an original founder of our collaboration. Instigator. So we'll try to be crisp and succinct here as we go through our presentation, and I won't take much time, but I do want to give you just a bit of some context, and then our students will give you some more content. So this class we call ETR 237. This class is what we call Industrial Electronics 1. It is what we would call a capstone class, or part A of a two-part set of capstone classes. 238 will follow in the spring. And this class is meant to culminate students' work here in the area of industrial electronics. And we focus in this class on industrial electronic processes. And in particular, we're talking about feedback loops. So processes which have feedback, and I'll show you that in a second, and the control of those processes through a controller to obtain a given what we call process variable. And so our goal is to talk about that generalized process, but then to apply it to particular use cases. And so our three students, Isaac, Christian, and Jonathan, each have applied the following to a use case. Here is what I'll call a generalized process control loop. So in this figure, what we're trying to do is, in a closed loop sense, meaning using feedback, we are trying to optimize a given process. And the key components of this process are what we would call a process variable, a set point, a sensor, an actuator, and a processor. And these act in unison in a closed loop sense, that is, with a feedback mechanism to optimize a given process. So for example, if we were to try to optimize the temperature in a room, the actuator that we might make use of might be an air conditioner or a heater, something that actually changes the temperature of a room. The sensor that we would use would be a thermometer, and the processor would be something that compares what that thermometer has measured to a set point. Perhaps the set point would be the temperature setting we want for the room. And so the computing of the difference between the process variable, which would in this example be the instantaneous temperature of the room, and the set point, which would be the desired temperature of the room, that's the closed loop process we're trying to optimize. And you can see in the top right depiction, the process variable as a function of time, with the set point being the dotted line, and an error, the difference between those two, epsilon, which ultimately we try to drive to zero. And so the things that we think about in this class are first, this overall process, then the effects due to noise. Noise is everywhere in all of these processes. It's in the sensor, it's in the actuator, it's in the processor. And so the contribution of noise to this overall process is an important feature. And then the timeline it takes for us to drive the error to a acceptably small error. So effects of noise, effects of time. In these projects, we imagine an ultimate system. For example, our first presenter will speak to the ultimate system of a three-dimensional printer, a 3D printer. A second talk about what he calls a water sluice gate, meaning a gate that controls water flow for watering crops. And then the third, an ice cube machine, a machine that literally makes ice as an overall process. And we emulate those ultimate systems. We're not building 3D printers. We're not building full scale anything. We're building what we call an emulator, something that's at a smaller scale that emulates the key features of the ultimate system. And we're using as a key building block for that emulator an M4 feather board. This is a low-cost, commonly used piece of electronics that we use with our students here to emulate analog digital control systems. And it's controlled by our PCs, by our personal computers, using software that is commercially available and well known, a derivative of Python. And so the idea is to use low-cost hardware and software to emulate the objective or ultimate system. And then, given that, to investigate particular aspects of this closed-loop process, to corrupt the set point with noise, for example, and see how the process variable is affected, or to imagine different time constants, what we would call a slow time problem or a fast time problem, and see if we can generalize some of our findings. And then in subsequent classes, these students will build something that's at a larger scale. So this is sort of the first step in a multi-step process where we're understanding the process, picking out a few examples that are important, the effect of noise, time, and then ultimately they will build something that actually looks like a 3D printer, a sluice gate, or an ice cube machine. So with that, I'd like to turn it over to my students and ask them to give us a talk, and I'll begin by inviting Isaac to speak. So Isaac, over to you, sir.
All right. Hello. I don't know if you guys can see me or not. Anyway, yeah. So the kind of original goal that I set myself for this project was to kind of emulate or create an almost 3D printer. I realize that this is a lot of text on one slide, so I will end up going over it in other slides. And the idea was that I use stepper motors to kind of emulate the movement of a 3D printer. So X, Y, and Z. I didn't get there. I didn't get enough. I didn't end up getting to quite that point. But what I did was I did something a little bit different. So I ended up, the bottom level, what I ended up doing was creating, as Dr. Cordella talked about, was a set point. And so the stepper motor would move to the set point, and then it would choose a new set point. This program that I made would choose a new set point, and then the stepper motor would step towards it. It would hit the set point and then move back down, and then or move to the next set point that it was choosing. So it was a random set point generator that the motor was trying to get to, with the goal of eventually being able to control where the set point is to move in X or Y or Z axis. But what I ended up doing was actually adding noise to that process, which I will talk about in a minute. So the hardware that I used was, as we said, the feather end board that was then connected to a DC/stepper add-on board so that it could be wired together, because the feather board is too simple to be able to do it directly. And then the CircuitPython was the backbone. And what I ended up doing, the end product for this class, was that set point generator, but it would add noise to the set point so that it would jump around a lot heavier than the original program did. And so it would choose a set point, and then it would choose a bunch of smaller numbers around that set point to emulate having some electrical interference or something in the motors to kind of get to those smaller numbers. This is more detailed into the actual program that I built. So it would do the full loop, and it would choose the set point. Those are kind of the same thing every 4 seconds. And then every half a second, it would then choose the noise. So what it ended up doing was it would choose one set point, which is just a straight line. And then the motor would get to it, then it would choose a noise around the set point. So then it would jump down, jump up, jump down, jump around. So I have a chart on the next slide. So as you can see, let's see if the mouse shows up. It does not. Okay. The blue line right in the middle, that's completely straight, is that set point that it chose. The orange line is the noise, the kind of small adjustments around that set point. And the green line is the stepper motor quickly stepping up, trying to moving to that point, and then the noise changes, and then it changes again. The motor goes to it. Yeah. So the conclusion is that it was possible to create this thing. And I actually, in having to rewrite the program to allow for the noise, it ended up creating a much more efficient program, which could be used as my next step to create a very efficient, controllable stepper motor system. Yeah, that's all I have.
Okay, that's great. So this was an example of the creation of noise that would corrupt the process, and then trying to identify ways to mitigate the effect of noise. And then as we build out in the next class in the spring, you can see the complexity of the system will grow, adding more motors, more actuators, moving in 2 dimensions, and building towards that objective system. Our next presenter is online, I think, Christian.
Hey, how's it going?
Good. And Christian's project is emulating a sluice gate, and ultimately there may be a more, what we would call a fast time problem that aligns with Christian's personal interests of automotive applications. But Christian, would you take over, please?
Yes, sir. Everybody hear me okay?
Yes, we're good.
Okay. So yeah, my project, I'm making a sluice gate. I bet everybody's wondering what that is, but it's pretty much just a gate blocking the flow of water to rows of crops. For hundreds of years it's been used, but for this project I wanted to automate it and use soil moisture sensors to lift and close the gate to reduce water consumption and reduce the amount of work required to grow stuff. So the process I used was do a lot of research, design a solution. I then wired up all my hardware, which you can see in that top right picture. I made a small model on SolidWorks and was able to cut it out on the 3D printer that we have in our shop. And there's a picture of that later. Next, this is the pyramid of what we were looking at earlier of the big time problem of wanting to water acres of crops. And in the middle of that, we have a motor and 1 moisture sensor. And then under that, we have a comparison for the slow versus the faster time, which I'll get to in the next slide. So the hardware I used a sheet of 3mm thick birch to make my sluice gate. I used a feather and floorboard, a soil moisture sensor, and a servo. And in my code, you can see over here that we start by having the sensor spit out a value, and then that is converted to an analog value. And then if that analog value is below a certain amount, the soil is dry, so it has to open the gate. And if it's above a certain value, the soil's wet, so you have to close the gate. Next slide, please. So here's a graph for my what I call the slow time project, which is the sluice gate. So I left it on for about an hour, and you can see these little dips of where the soil started to drop in soil moisture, but then the gate opened, and when that happened, I just spritzed it with some water, and then the soil got moist again, and then it shut the gate. So now to talk about the fast time problem that I've been alluding to this whole time. I want to design a nitrous controller, which is an application for cars with big turbos that take time to spool up. So within that time, you use a chemical called nitrous oxide, and you spritz that into your engine, and basically it causes a bigger boom, but you want a very controlled amount inside your engine, otherwise you'll blow it up. So it's a very fine balance of your RPM is going up, so your consumption is going up. So that's that red line is your RPM. So that's what we're trying to catch up to. And then that green line is the mix of nitrous and gasoline. So if you want to go to the next slide for me. So some conclusions I came to while working on this. The simpler, the better. The code I had used to be about 3 times as long and accomplished the exact same thing. But I found that it was much more reliable to have one line of code doing one thing than trying to have like 6 lines doing like one thing. And yeah, I found that I was successful in being able to control a gate using a soil moisture sensor, and that it was a lot easier to break it into smaller sections than try and take on everything at once. And that's my model of the sluice gate as well. Next steps, I already kind of talked about this, but working on that nitrous controller, which is a very similar problem to the sluice gate, just happening much faster. And then possibly introducing a flow sensor to the sluice gate problem. That's all I got.
I think one point I'll reinforce from that talk is the building block nature. Keep it simple and keep it small and manageable. We did have during our semester this semester a guest lecturer from a local power company, and he talked about all of the processes that they have at their natural gas power generator. Thousands of processes. Consider this as one small process. They have thousands of them. But his point to us was each one of those is simple, and it's a simple building block. So begin with simple things and then add complexity. And so I think that's been reinforced through this work. Our third and final presentation is from Jonathan Waters, and he is emulating an ice machine. Jonathan?
All right. Hello, everyone. My project for this semester was emulating the ice machine. So as Christian and Isaac said before, we used the M4 feather board to create the process control loop. First, I had to figure out what sensors I needed and what motors I would need to control the actuators in order to get this full loop going. What I came up with is I needed a thermocouple, which is going to measure the temperature, a photo sensor, which is going to measure how much light is getting in for when the ice machine is actually full and when it's not full, an ultrasonic sensor, which measures distance, which is pretty much I use for my depth gauge, and then 3 DC motors. So after that, I had to figure out how to wire it up and get example codes of how each sensor works, and then get the motor code to figure out how that to get running. At top right is a picture of my hardware all wired up. Kind of hard to see, but as a result, mine was more determining time dependencies of the process variable versus the set points. So this was my system process loop. As you can see, we have the yellow is all my sensors. The dark blue is all the actuators. So once the photo sensor senses there's no ice in the machine, that's when it'll open up the valve to let the water into the container. Then when the container gets to a certain amount of depth, then it'll shut off the water valve and then activate the cooling fans. As that time keeps going, the thermostat or thermocouple will measure the temperature. Once it reaches that certain set point, it's going to activate the dumping mechanism and shut off the fans. Then it'll dump it into the ice machine, and the photo sensor will not have as much light coming through because it's full, and it'll shut off all the stuff. Overall time is about 45 minutes, so it takes a while for the water to cool down and get to that freezing point. So this is my system description. To emulate the ice machine, where it takes the water and freezes it in a certain amount of time to be more efficient, was the main thing I needed to try to work towards. So as I said, I had the 3 DC motors to control the water valves and dumping mechanism and the cooling fans. and then create certain set points for the sensors to read when the process variable gets to the set points to activate the actuators, the bottom part. These are all the sensors that I've used in the motors and the featherboard. A little snippet of my sensor software that I got online from Adafruit. So I got my set point is 5,000. It's going to read how much light is coming through, or the sensor senses. And when it gets to that certain set point, then it'll turn on the motor. This is my temperature software. Here, this is where we have a little absolute value. So if there's the temperature reaches 5 degrees above the set point or 5 degrees below the set point, it'll actually activate the motor, so it doesn't have to reach that certain set point to turn on the motor, because temperature fluctuates so much. So it makes this a little more efficient that way. This is my ultrasonic sensor, which is measuring the distance of how far something is compared to the sensor. So when it gets to that set point, it'll say water is full, and it'll stop the motor. These are little snippets of all my plotters. So the green is my set points. And as you can see, the photo sensor, I didn't have that much light coming through. No, actually I had too much light coming through. So it's a little further from the set point. Temperature one is around 70 degrees, and that's pretty spot on with what the process variable is. Then the sensor one is, I was playing with it when I was activating it, so it's a little crazy right now. So all in all, my conclusions, pretty much what Christian said, making everything simple. Instead of doing everything at once, I broke down every sensor to what actuator it was doing. And that made it a lot more easier for me to understand what was happening within the code. And with the temperature set points, with the convergence band, so the temperature is either, I could make it 2 degrees, 1 degree, 5 degrees, however much I want it to be. It actually makes it more efficient and makes the system less sensitive to noise because it happens all around. My next steps will be to put all the codes in at once, because I never got a chance to do that, to see how they all work together and see if one doesn't work compared to the other code. Try to figure that out, which I'll do next semester. Try to just make it more efficient. And I think that's all I got.
That's it. So this is a good example of creating a way to mitigate or address the problem of noise. That is through the use of what we would call a convergence band around the set point. In this example, plus or minus, say, 2 degrees. So that as noise impacts the system, the effective noise is not so dramatic because there's a band around the set point that is still allowable. And that's a way to mitigate the effective noise. So these projects have started us down a path where we've talked about the same process model, the thing I showed you up front, but now we've applied that process model to 3 different applications. And what I believe we've discovered is they all come together in many ways. They come together in terms of robustness compared to noise, time to converge, and ultimately we'll speak in the next semester about higher degrees of machine automation to automate these processes. And with that, I believe that's the end of our presentation. Does anyone have any questions for us?
I have one question, Scott.
Yes, please.
I just Googled this featherboard. It works like maybe like an Arduino or just like a simple proto board?
You want to answer that?
Oh, yeah, so
on.
these, hi, I'm Will. I'm a lab technician here. The feather boards are effectively similar, very similar to Arduinos. They're a little more powerful, have a few more other capabilities that are really helpful in terms of process control. But yes, they're very similar to Arduinos.
Okay, thank you.
Yeah. And we've used free software based on Python, and in some cases we didn't create all of the software. We reused software that existed, so that was very efficient, and then we could tailor the software to our application. So we're not trying to become software experts in this class. Rather, we're trying to integrate software and hardware and do so efficiently. So it's been a fun semester. Thank you.
Thank you.
Maybe I have another question. Like,
course.
PVCC usually is at the first 2 years of to get a college degree, or that's the kind of program. But I'm thinking that maybe your electronic engineering technology program is like a separate training courses, or it's part of a degree, like a bachelor degree or something.
I think it's best to be answered by my boss, Ken. Ken, would you speak about the program?
So our program is a little bit unique at PVCC, as you concluded. We're an applied associate's degree. So in the United States, we have associate's degrees, which are 2 year, and we have bachelor's degrees, which are 4 year. So ours is an applied associate's degree, and there's several other. We have some healthcare degrees like that. We have some information technology degrees like that, but they're not true transfer programs. They're meant to basically get people skills rapidly in 2 years. That said, we actually do have a transfer agreement with one university in the state of Virginia that will actually give you a bachelor's degree in engineering technology. So yes, it's a little bit different than your traditional path.
Okay. Don't be shy. To our students, I'm asking.
That's better. Okay. All right.
I was a little bit surprised about the how do you pronounce it? Sluice gate?
Sluice gate. Yes.
No.
That will be like next semester. That will be used for a real crop plantation, or is just
Well, and I'll let Christian speak to that. It's his project, but frankly, what we're trying to do is set the stage for a larger scale effort. And that sluice gate problem could be done at a larger scale with more sensors, something, like an aquarium on a big table, that kind of a thing. Or, and this is where Christian's personal interests enter, as an automotive guy, the analogous problem is the nitrous oxide fuel injector motorized automotive system. So we'll negotiate what we do with this, but we've sort of set the stage for another conversation. So Christian, would you comment?
Yeah, it would be really cool to actually make a working sluice gate with this idea, but I don't know. Though the one I made is only a couple inches tall, because the servo can only really move so much weight. But I would love to actually make it a real thing, because I think it could truly save a lot of water. But also, like Scott said, Mr. Cordell said, could be applied when you switch out variables, like instead of soil moisture, you're instead looking at engine RPM, and instead of how much water is going through, you're looking at oxygen going into the engine, and then you take all those variables and switch them out, and all of a sudden you have a completely different project that's still pretty much the same.
And I would offer the openness and interest in collaboration around these topics. If there were things that you guys were interested in doing jointly, perhaps that's something we could talk more about later.
Yeah, of course. I think that this this type of work is really interesting, and some of our students from electronic area probably could work with you in different sort of projects.
That'd be great. Great fun. It'd be fun to build something and try it out, experiment.
Yeah.
I would like to say to Christian and the other two students that presented their projects that our students that are here today, they are not English. Most of them, they're not English fluent because I don't know if I'm saying it okay, because they don't learn English as a second language at their school. They just learn how to translate technical related text. So to prepare for today, they're doing a big effort, but probably they understand, but it's very hard for them to prepare to say what they're thinking. So it's not lack of interest, it's just that it's a little hard for them.
And we thank you for using language that we're familiar with. I think it would make it very difficult if we had to do what you're doing. So thank you very much for that.
So if no one's want to make another question, it's okay if we move to the Otto Krause project.
Yeah, let's start.
Yes.
Okay, so thank you for being part of this exchange program, for being here, and today's topic is the Energy Rehabilitation Project at Otto Krause, coordinated by architect Mariano Salazar. I am I'm the language teacher, and I went to Charlottesville back in 2015, and I'm a big fan of this exchange program, so that's why I'm here. And so let's start. I will present. Okay, so the students will talk, and then at the end, there'll be time for questions. Now you'll meet our fifth-year students. Now they will introduce themselves.
Hi, my name is Marina. I'm from Construction Engineering Technology major.
Hello, my name is Ilan. I am from Construction Engineering Technology major.
Hi, my name is Sofia Wash. I'm from Construction Engineer Technology major.
Hi, my name is Julian. I am from the Electrical Engineering Technology major.
Hello, I am Julián Barrenuevo. I'm from Electrical Engineer Technology major.
Well, I am Agustin. I am from Construction Engineering Technology major.
So now they will start presenting the project.
Our school was founded by Otto Krause, who was an engineer. It is the earliest high school college specialized in engineering technology in the country. The school operates on a 6-year program. The first 3 years of the program, called Ciclo Básico, Basic Cycle, provides essentially a preparatory high school program on science and technology for youngsters that have completed their elementary education. The final 3 years, called Ciclo Superior, Upper Cycle, provide the equivalent to a college education degree in engineering technology. The school offers 6 technology majors: chemical sciences, information technology, construction engineering, electrical engineering, power concentration, electronics engineering, and mechanical engineering. Several requirements were taken into account at the time of choosing the right building for the energy sustainability project. For example, the building should be part of the Buenos Aires Historic Quarter and a historical heritage building. The school met all these requirements and also had a decisive point, which is that the students have technical knowledge and abilities to take part in the project.
Well, the project that we are going to present today is called Energy Rehabilitation at Otto Krause School. The project began in August 2021 and it was carried out together with teachers and students from the majors of construction, electrical and electronic engineering technology. Furthermore, the following government organizations have participated in the project: Institute of Energy and Sustainable Development, National Atomic Energy Commission, General Directorate of Heritage, Museums and the Historic Quarter, Green Schools, School of Architecture, Design and Urbanism of the University of Buenos Aires, and the School of Engineering, Infrastructure and Environment of the University of Edinburgh in Scotland.
The purpose for our school is to be able to carry out the energy sustainability project on the Otto Krause building. The aim of the project is to reduce energy consumption by more than 60% in order to be able to help reduce the effects of climate change, improve the health of the people that use the building, and above all, they acquire knowledge and learn how to use it.
As students of construction, electrical, and electronics majors, our goal is to learn from the training courses taught by professors from the United Kingdom and the CNEA, so that in 2022 we can implement all the information we have acquired in the space of professional automation. One of the possible problems of windows and doors, which are acquired all, evaluating their lapentry and glass, and that way will guarantee good acoustic and thermal inclusion of workshops and classrooms.
Well, a series of 10 training courses were carried out throughout the project on the Meet platform in order to acquire the necessary knowledge. We learned the necessary concept together with the corresponding exercises. With these seminars, we have learned knowledge and importance of the energy efficiency, environment, inspection, analysis, and understanding of the energy performance of the building to be improved, implementation and learning of 2D plan design programs, 3D models, and data collection in the Excel environment, notion of environment simulation programs, calculation of energy gains and losses of materials, uses and functions of measuring instruments, electrical devices, enclosures, air circulation and humidity of the different parts of the building, analyze the water electricity consumption bills, knowledge of various indoor air conditioning systems, recognition of pathologies present by the building to be analyzed, that is to say, humidity, fungi, or fissure.
Well, in order to apply next year what we have learned at the school in the training course, which was a smaller scale project based on our homes, several steps had to be followed in order to reach a conclusion. These steps are analyzing electricity bills, making an energy diagnosis, which involves documenting each electrical device in our homes in order to see which are the significant uses of the energy, comparing energy consumption in 2020 with the estimated energy consumption, adopting measures for those significant uses of energy, carrying out a survey of our homes, which included metrical data and a 3D model, choosing 5 strategies for the face walls, 2 active strategies, and 1 renewable, and finally, reaching a conclusion. Each of us arrived at our own conclusion. As I said before, this helped us to understand the issues we had in front of us before putting them into practice in an easy way, and it prepared us to be able to apply them on a bigger scale during the next year.
During 2021, we have carried out the metric survey of the school, studying the building and collecting information in AutoCAD files to update the school construction plans. Some walls and doors measures did not coincide with the ones we had. Therefore, we had to measure the wall thickness and change the functionality distribution of some classrooms. These AutoCAD files were the basis to make a 3D model of the school in the Revit program. A teacher trained us to model in Revit under the protocol used in Argentina.
In 2022, the analysis of active and passive systems will be carried out at school in order to perform a new remodeling on both systems. We are going to take corresponding gas and electrical measurements that are provided to the school so that we can compare the numbers of 2021 and 2022 to know the efficiency of the work done. The financing of the project will be charged the city government.
You're muted.
Yes, so we have big expectations for 2022.
Yeah.
This is very good. Excellent. I had no idea. This is a very large scale project. What do you see some of the impacts from the work that you're doing? What's the outcome that you imagine?
Les preguntan, hello, my name is Maria Andrea,
Yeah, well,
I'm one of the teacher of English, and well, I will try to translate just for you to have an idea and well, just to help them. Les están preguntando cuáles son las expectativas de logro a largo plazo. Okay.
Well, by the next year, we are expecting, based on our analysis that we are going to make, to reduce the consumption of the energy and have like use renewable energy like solar panels and all that. So we are expecting that the energy that today we are wasting is not a lot, but well, we have to see the next year.
So you have some sort of budget of how many watts of power for solar or electrical or different sources of energy or losses?
I've learned a little bit because I've been talking with the students. I know they're like in the early steps of these projects. They're like learning how to recognize some pathologies of the building and to learn how
I think they are trying to have a kind of a survey on items like consumption, gas consumption, electricity, and the kind of watts they have using because there are some laws everywhere, and well, and they're trying to reduce as much as possible. This is what
Yes.
the project is trying. They are just at the beginning of that.
Yes.
The idea is to carry out a big scale project with these governmental institutions like CNEA here in Argentina, the National Commission of Atomic Energy, and those organizations in charge of the history of our school and history of our town here in Buenos Aires.
Well, maybe I could get my friend Ken to say a word or two, but what immediately occurs to me is that we are building a brand new building here at PVCC. They haven't yet broken ground, but they will. And in something like 2, perhaps 3 years, we will have a new building, and that new building will house our program. And it would be fascinating to me to use that as a use case, as an example application of some of the things that you have done. So that's immediately occurs to me. And the second, and then I'll ask Ken to comment, is for our class, our next industrial electronics technology class, which follows this one, there is a purposeful community service theme that we must work towards, that we're doing something in favor of the community's interests, not just our own parochial interests. And so again, I think energy conservation, energy awareness, optimization, all of those things, I think is relevant. Ken, would you comment?
Yeah, as Scott said, we're getting ready to break ground on a new building. What's fascinating about this building is that it's the first building in our state, in Virginia, that the government will build that's net zero. So basically what it's going to do is it's going to have enough solar and geothermal to actually control all of the heating and cooling systems, as well as all the electronics. And when you think about a program like ours, we actually have a lot of large machines. So the ability to actually power all those machines with solar is quite the task, and it's going to be quite impressive to do this. So maybe it's something, as Scott said, as we get this online, maybe we can share with you, and you can do some analysis on it, or look at whatever. I'm sure there will be a lot of control systems. I don't know a tremendous amount about it, but I think it's an interesting project for the future.
Yes, sure.
Thank you. Yes, that's very instructive. It's very good for us. Yes, we would appreciate just to share knowledge among us. This is very important nowadays.
Absolutely. We're
Well,
excited.
I think this is a great opening for a longer and more productive conversation. So first, thank you for that. And this is
Thank you.
Perfect timing for us, certainly for me, getting ready for the next semester and to try to align a few things without trying to make it too tightly aligned, but at least loosely aligned around a few themes would be certainly helpful to us. And I hope we would be able to be beneficial to you as well. And we always learn new things when we hear new voices. So thank you.
And also that was the main goal of this video conference when John Donnelly and Patricia Grosso first started talking about this. So, well,
yeah, I think this has been quite successful, and I think it aligns with the original intent of these dialogues. Would you comment?
Well, things have expanded. We started with the student exchange, the faculty exchange, and now the Spanish program started to have link-ups. And gradually the engineering program got involved, which is essentially what they do. So yes, look forward to growing, and
we'll keep you informed of how we're moving forward, and I hope you'll do the same, and maybe we can schedule another one of these conversations at the right time in the near future, just to keep the momentum going.
Sure. And also, well, we
Definitely.
would like to talk like inside our school with the electronic engineering technology major, because probably they will have their curriculum is quite, there's a meeting point in all those in the curriculum. So
Good.
They share the same objectives as you have there. Those a kind of measure between of the objectives are very, very similar in those positions. So it would be a good idea just to have a talk with them in order to have a meeting with them, and as regards the electronic part of this conversation, discourse.
Yeah. I think for us, and it's just, and any of you all are welcome to comment, we're pretty good at doing things on the bench at a small scale. Those emulators that we've talked about, those can be done inexpensively and without too much heroic work, if you know what I mean. To get to the next level of scale and the next level of sophistication, that's a heavier lift. And that to me is a great opportunity for joint collaboration. We may have some shared test bed vision where you might build a piece, we might build a piece, and then they come together so that it's not so difficult for one of us to do. It's easier when we do it together. So that to me is sort of the next hurdle for us, is getting in that next level of sophistication. So I think a discussion with our counterparts on your side about that, and not just down in the weeds about feather boards and actuators, but rather something at a next higher scale, that would be, I think, would be very productive.
Well, we can.
Some question, Paula?
Yes, go ahead, Henry.
Students, are they all from construction engineering?
No, would you like to present again?
We can hearing well.
No, my question is, the students that are on this meet today, are they all from construction?
No.
No. There are three majors involved, like electrical, electronics, and construction. We are just three.
But all centered around the project of energy conservation. So it's really kind of centered around the building per se, not about the A's and B's and C's of electronics. It's more like, what can they apply to the redesign of the energy systems in the building. So that's really why this is, and I may have to explain to my audience here that with the newer curriculums that came up in the last few years in Argentina, they put a lot of emphasis on multidisciplinary programs, like at the last of the 3 years, where different departments work together on a project where they all contribute to the project, like in the real life. It's like a simulated project, simulated company, just bringing in their knowledge, like a capstone project, by combining as many as the departments as they can.
Makes sense. Yeah.
And this is a little bit like that.
Yeah,
it's
that
very
comes through
different.
very clear.
But I'm sure there are people that are doing what you're doing.
Well, and maybe the goal is not to find people who are doing what we're doing, rather to find you who are not doing exactly what we're doing, but to merge them in some
I know that
coherent way.
I know they teach closed loop control.
I'm sure they do.
I know
sure
they do.
Yeah.
I know that's a fact. But
I like the idea that we're project oriented, we're outcome oriented.
Yeah.
Now all the disciplines support that bigger outcome.
That's what this is.
Yeah.
As a matter of fact, my question to you is, is this done in what times are you using up? You're not using up any of the theoretical classes. Are you using the workshop classes for this, or is it even outside of that? So it's all, Mariano, you,
Well,
Maximiliano, Maxi, you can probably answer that.
Yeah,
No
maybe
sé,
if Agustin could want to talk,
Te
but
lo pregunto en
no, no, no,
castellano.
no, no.
No,
Hablamos
it's
No, no.
se
clear.
entendió. It's clear, yeah.
they are using their 3 hours. It's
Okay,
like an
so
extra programmatic program, and they are working in between classes and in the afternoons when they weren't in the school.
so it's like extracurricular, really, but it's also done.
Yeah, probably
Yeah.
the next year they work in this project inside the professionalizing practice. I don't know the name of the.
Clasification samples. Okay.
Yeah.
This is
So
where
it
it's
took
part of the
place
program.
in that class,
Okay.
but
They're
this
using
year,
some of that time, but you're using additional time that's totally outside of classes, outside of programs.
yeah, of course.
Yeah. So it's a combination. Yeah, got it. Okay, thank you.
Well, what would you recommend we do next? I'm very
Well-
eager to keep coming together. What could we
Yeah.
do next?
I was thinking now we're students are they're already on their summer holidays, so they're here because they wanted to. But we'll be having all January and half February. That's our summer holidays. So probably we can schedule. I can write you again by the end of February. We know you will have your summer holidays starting probably the end of May.
Right.
So we know we have that time period to work with you. So
Okay.
I will make the link between electronic engineering technology major and PVCC. Well, and
But
everybody
I
at
also-
Krause to keep working.
Yeah, to the point we just discussed here, though, that Henry brought up, that collaboration around the bigger goal is, to me, a real strong motivator. I would like to meet our counterparts in your program, but to me, the thing that's very interesting is to see how we serve as one slice of the pie and there are other slices that come together. That to me is very powerful. And I think that probably is at the right level, PVCC, your organization, that bigger goal is what we're talking about, not down in the details of electronic closed loop systems.
Yeah, sure.
Yeah. But yeah, we'll look forward to it. That'd be great. I respect your time. I don't want to take it longer than you wish. We'll go as long as you want, but I see we've used the hour. How would you,
Yes.
how do you want to proceed?
Maybe if you want, we can say a goodbye, and then if I can stop recording, and then if we can stay the ones that want to keep talking.
Okay, that sounds like a great plan.
Okay. Okay, so
Anybody else have anything to say? No? Okay, great.
If I can add something.
Of course.
So
Just
thank
listening
you.
Hold on, 1 second.
Listening to this and how to go forward, I see 2 tracks. I see one is your project on modernizing the building for energy conservation, which will tie in with what Ken proposed, to look at the blueprints, the plans of the new building, so that you see some technologies that you may be using on your building incorporated into Piedmont's new building. So I see one that is oriented towards what this presentation has been like, closer. On the other hand, I know that the electronic guys have all kinds of cool little things that they've done over the years. I don't know what they're doing lately, but going back just a few years, they built their own 3D printer from scratch. And they built some kind of mechanical electronic hand, right? That they showed me back when, and I don't know what they're doing right now. But I think that it may be worthwhile to have some meets that deal electronics to electronics, and then the other one, which is more global about energy conservation and the technologies that go into that. So I think you probably have 2 tracks to work on. That's what occurs to me. Now, you guys decide what you want to do. You know, I'm just a troublemaker.
Ken, do you want to say any parting comments?
I just appreciate everybody's time. This is a really great, I know this is kind of a new starting point for us. I'm taking over the program, and Scott's been quite involved. So we really appreciate this relationship. We're excited to continue it. And I'm sure as we go through this, we'll figure out some kind of a regular frequency that works between the schedules, being in different hemispheres. But absolutely connecting our counterparts and talking on that level, but talking on a larger, kind of project level as well is really fascinating. So we look forward to working with you more.
Okay, so let me say goodbye, and then, so thank you all for being today here, and thank you Miriam, Andrea, Graciela, Claudio, our Otto Krause English teachers, for being a huge support and lending your time. Special applause for our students who prepared their speech. This took some preparation, and they were happy to do it even though they're already enjoying their holidays. So happy holidays to all, and we'll keep in touch. So I'll stop recording.